Welcome to my presentation on optimal control for electromagnetic haptic guidance systems. This work was done with colleagues at ETH Zurich and New York University. We propose a novel time-independent control strategy for electromagnetic haptic systems. Pen-based interactive systems that feature haptic guidance support users in a variety of applications, such as drawing, sketching, or CAD design. The goal of such systems is to enable users to draw higher complexity shapes with less effort and higher accuracy, or to support users through virtual haptic tools such as rulers or guides. Crucially, such systems aim to strike a balance between giving users a strong sense of control and agency. Here we see a prototypical version of our system, how it can be used and the different components of the system, such as a pressure-based tablet and an electromagnet mounted on a bi-axial linear stage. Yamoka and colleagues proposed Depend here at WIST in 2013. Their system uses a permanent magnet on a bi-axial linear stage. However, they use an open-loop controller. This means that the user can only react to the system and not vice versa. Due to this, the user needs to passively follow the actuator. Corris and colleagues proposed Katip, which is a haptic visual guidance system. They use, unlike Depend, a closed-loop control strategy. However, this is a time-dependent strategy. This makes adapting to the drawing speed of a specific user, for instance, impossible, thereby still limiting user autonomy. Basically, both systems consist out of a desired path. And furthermore, there is the current pen position. On the path, there is a set point, or basically the point where the user should be, the desired point. The goal is to provide haptic feedback from the pen to the desired point. The easiest way to do this is to have the electromagnet on top of this line. However, due to the sharp decline in electromagnetic force, the electromagnet needs to be sufficiently close to the pen. Let's discuss the difference in behavior of the system between open loop and time-dependent closed-loop control to really understand the problem at stake. On the left, we see an open-loop controller. With an open-loop controller, we can see how the setpoint and electromagnet move independently from the user position, likely being even so far away that a magnetic force cannot be perceived by the user anymore, rendering the system only useful if the user is fully compliant. On the right, we see a time-dependent closed-loop strategy. Although the desired setpoint behaves in a similar fashion as in the open-loop controller, the electromagnet stays within actuation range of the pen. However, since the setpoint move, this can lead to haptic feedback in the wrong direction, such as in these three here. From a user perspective, the goal is to have assistance during pen-based tasks. This feedback should be natural, and the control should remain with the user. From this goal, we can deduce two important factors. Natural would indicate that the tool needs to be untethered, as well as minimally instrumented as possible. Electromagnetism is a logical solution for untethered tools. With control, the system should adapt to the user and not the other way around. This gives rise to the question on how we can control haptic feedback systems, especially electromagnet-based, to find a balance between haptic feedback and user autonomy. To this end, we propose a real-time closed-loop control approach that allows users to retain agency and control while being assisted by an electromagnetic haptic guidance system. We contribute a novel optimization scheme that enables formalizing this problem. On the right, we visualize how with our control strategy, the setpoint and electromagnet are dependent on the user. In the slow motion shot, we show why open loop controllers provide problems, especially in magnet-based systems, due to the sharp decline in magnetic force over distance, extreme snapping behavior can occur. We can see that this becomes fluent with our method. In our paper, we make two distinct contributions. Our first contribution is the novel control strategy. The second contribution is a prototypical hardware implementation, which allows for a variety of applications and user evaluation. Let's first discuss our control strategy in more detail. In essence, the system consists out of an electromagnet, which has both a position and intensity, as well as a desired path. Furthermore, there is the current pen position of the user. The goal of the strategy is twofold. First of all, to minimize the distance to the desired path. And secondly, the actual force should be the desired force, meaning the correct intensity and the correct direction. This is a hard problem due to the snapping. Our method needs to be fast and precise. Our control strategy is based on model predictive contour control. This is an iterative method with a receding horizon. It is time independent as well, and is often employed in quadcopter control or CNC machines. Basically, in an MPCC, we minimize a cost term. This minimization is constrained by a systems model. We are trying to find the best inputs and states of the systems. These are u and x relatively. For an input, you can think of acceleration, whereas state is position, for instance. In our case, we have three cost terms. The first cost term finds the closest point on a path with regard to the user current position. The second cost term promotes overall drawing progress. And the last cost term covers the position and intensity of the electromagnet, which results in a force onto the tool. Let's first discuss the cost that governs the path following. For the path following error, we do not have to take into account the electromagnet. This leaves us with just the path and the pen position. The goal is that we find a point on the path that minimizes the Euclidean distance between the path and the pen. However, this is an optimization problem on its own, and time-wise infeasible to do in an active system. And frankly, since the gradient is not always present, this is impossible. Therefore, we introduce two new lines. The first line, the dotted, is the tangent at a point on the spline. The second one is orthogonal to it and intersects with the pen position. Given this, we try to minimize the lag error shown in red. This is the projection of the pen onto the tangent. The second error is the contour error, denoted in blue, which is the line orthogonal to the tangent. If the lag error approaches 0, the contour error approaches the Euclidean error. Then we simply sum the two to get the path error. The path following cost gives us an approximation of the closest point on the path. However, natural correct would not per se go towards the closest point, but slightly forward. This is where the progress term comes into play. The desired point can also be defined in terms of theta, or the relative position along to the path. Here, a higher theta means that it is further along it. Therefore, we can generally write a higher theta. Finally, there's the force cost term. In our case, the magnet is always attracting the pen. This happens from a center of a permanent magnet embedded in the pen in a straight line to the center of the electromagnet. For sake of simplicity, we will forget about the Z component of this force. This force is mainly depending on two factors: the distance between the two magnets, as well as the intensity of the electromagnet. The intensity can be controlled by the current that is used to power the electromagnet. This describes the actual force. The second element of our cost term is the desired force. This force is in the direction of our desired point on the path. The final cost term then is the square difference between the desired and the actual force. The system will change the position and intensity of the magnet in such a way that this is minimized. Calculating the force between two magnets is not straightforward. However, crucially, this enables real-time control. For those who are interested, we derive an analytical equation to do so in our paper. Now that we discussed our proposed method, let's take a look at the hardware we implemented on. The system consists of an electromagnet mounted on a bi-axial linear stage. The choice of both is not trivial. We used FEM analysis to inform our magnet choice. This linear stage needs to provide enough force for fast accelerations. The system is agnostic to the tablet that is used to determine the pen location. This can be pressure-based, thereby allowing for pen and paper, or tablet, which allows for visual feedback. Furthermore, the stylus and pen used need to be augmented with a permanent ring magnet. With our proposed method and prototypical hardware in place, let's test it on users. We did two experiments here. First of all, we tested our system with end users on general accuracy. Secondly, we used a set of different users to compare control strategies. For the comparison with different strategies, please refer to the paper. Let's discuss the accuracy of the end user. We asked 12 participants to draw 6 different shapes with and without haptic feedback. The users received minimal visual support during this task, here denoted in red. The order was determined by a Latin square, so that each participant drew half of the shapes first with haptic feedback and the other half without. The order of the shapes was also randomized. Here we see a selection of results, 1 per shape. The orange is with haptic feedback and the blue without. We did not apply any filter on these, and these are raw points. The video is sped up with a factor of 4. Notice how the users with the feedback are staying closer to the target trajectory. When we take a look at the data, the straight line is the only result that is insignificant. The distance error here is the distance to the closest point on the path. In all cases but the line, we can see how the tails of the without feedback cases are significantly longer, which is an increase in maximum error. Overall, our systems make users up to 2 times more accurate. For more details, please refer to the paper. So what we can learn from our user test is that more complex shapes benefit most from feedback. Furthermore, notice that users, due to remarks they made during the experiment, are still limited by the speed of our system. And finally, overall people improve their accuracy. Now that we have taken a look at the evaluation, let's discuss potential applications. As shown here, one of the applications could be to help users with calligraphy. A second application could be to help people with outline and inking of complicated sketches. In this case, a dragon is drawn by a novice user with no drawing experience. Notice how the system can deal with different line segments and the lifting of the tool, as well as the swapping of the tool. These illustrations are final results drawn by the same user. The system here has the same settings. This illustrates how the user is still guided back to the same primitive shapes, yet they remain to have creative freedom. Finally, we show a use case with visual support. Here a user is manipulating virtual tools in order to support them with the design of a chair. Let's discuss our findings and head towards a conclusion. In our interviews, some users indicated that they had the feeling that their drawings without feedback were more accurate once they had experienced haptic guidance. This hints at the possibility of short-term muscle memory when using our haptic guidance approach. In terms of hardware, the speed of the employed linear stage was a limiting factor, without which users would have been able to complete drawings and journal inputs faster. In this paper, we have proposed a novel optimization scheme for electromagnetic haptic guidance systems based on the MPCC framework. Our approach balances user input and system control so that users can adjust the trajectory and speed on demand. We implemented our method on prototypical hardware and finally evaluated the system with users. All blueprints and code are available on our website. Thank you.